All set now? Okay, thank you, Aman.
Yes, ma'am.
Oh, so sorry. So yes, today myself, Dr. Jaspal Kaur, I will be talking about applications of information theory, spiked Wigner model, MMSC, and some mutual information applications. So I warmly welcome all the present participants to the GAN course day 3. So we have been talking about information theory from last 2 days. We already know it is a mathematical framework for quantifying information, communication and data compression. Addresses the amount of information which is contained in a message. So we try to quantify the amount of useful information. We try to identify how efficiently this message can be encoded and compressed. So we try to understand how reliable information can be transmitted over a noisy channel. So there are multiple applications we will see today in which we can apply all the concepts of information theory and all the mathematical frameworks that we have been studying and that we will be studying in the rest of our lectures. So these are the key concepts. I will quickly take you back to the entropy, which we have seen it is a measure of average uncertainty randomness in a random variable, and we have already seen the formula to derive entropy, which represents the amount of uncertainty or amount of noise in a random variable. And the mutual information, which is denoted by I, is identified as the amount of actual information present in one random variable which contains information about another. So it is represented as I of x, y, where it is represented as a differences in the entropies, entropy of x and entropy of x given y, which is multiplied with the mutual information. And then we check the channel capacity, which defines the maximum rate at which information can be transmitted with very low or minimized error. So that is the main objective that we have to follow in majorly in our signal processing systems as well as in machine learning applications, where we try to transmit the information. We try to the objective is to optimize the information transmission at a maximum rate with a very low or a minimized error. And then we talk about redundancy and compression using structure in data to reduce the number of bits. So this is what we follow in our case. The number of bits needed for the lossy or lossless compression. So we try to reduce the redundant data in the network. So we will see, already we have seen much of mathematical modeling of information theory and Spigner models. So now we will see how information theory is useful in communication systems. It has wide applications in machine learning, data compression, neuroscience and genomics, where we try to identify the information bottleneck and try to identify how we can apply information theory concepts in identifying the patterns from the gene interaction detection or in any neuroscience neural information transfer models. So this is the example that we have seen in spiked Wigner model, where we try to represent the model with the notation where we have a signal and a noise. So we try to identify that how well we can represent information and how well we are able to identify the noise out of signal, which is denoted as Z is a noise, and we try to identify a matrices representation where we have x transpose and lambda is a coefficient. So we see a wide application of spiked Wigner model in PCA, that is principal component analysis, in where we try to detect low rank signals and we try to identify the major component of a signal which can represent the entire signal and can really save capacity and can represent a better representation of a signal, representing the major components of a signal, and again we try to omit the signal that represents less information. Then we have random matrix theory, which has spectral phase transitions and a statistical detection, where we will see signals versus noise hypothesis. And then we have unsupervised learning, where also we can apply a spiked Wigner model. So this is all we see. We'll see random matrix theory and some more models where we can apply these models in form of in our future lectures, in form of all the mathematical derivations. So talking one by one, the principal component analysis, it is generally referred as a dimensionality reduction technique, where we try to extract the dominant patterns, that is the major component of patterns in the data. So in high dimensional data, we often observe a mixture of signal and noise. So our data contains both. It has some signal part, it has some noise part. So we try to identify how we can maximize the presentation of information in a signal by identifying the noisy signal, and we then remove this noise part from the signal. So this PCA helps identifying spikes or low rank signals which are embedded in our noisy observations. So this detectability depends upon the strength of a signal and the eigenvalue separations. So this is another concept that we have seen, that is minimum mean squared error. So we see a minimum mean squared error also as a key concept in information theory, and it has again wide applications in signal processing systems, in machine learning, in neuroscience, in cognitive abilities, and in many other unsupervised, identifying patterns from unsupervised data. So the key concept lies here that it derives the relationship between mutual information and estimation of accuracy in a noisy communication channels. So we try to estimate the random variable given another random variable. So we try to estimate the input signal based upon the given noisy output, and we try to identify that how we can derive a relationship between mutual information and estimated accuracy. So the best estimate is one that minimizes the mean squared error between the estimated value that we try to predict and the actual value that we take. And after this, we say it is a best estimation that we have identified. So we use the concept of mutual information here. Mutual information quantifies the amount of information that one random variable contains about another. So in the context of communication, we say it represents channel's capacity to transmit the information reliably. So this mean square error formula sometimes is referred as a relationship between the mutual information and MMSE, which is minimum mean squared error. So it's the derivation of mutual information with respect to signal to noise ratio, which is equal to the half of minimum mean squared error. So we have derived these derivations previously with Professor John Barbier. So I thought of conveying the theoretical part and the applications part of these derivations that we have been doing from last 2 days. So if you see here, the application part, when we try to represent MMSE in form of an equation, we try to identify the estimators. So it can be a measure of quality, it can be a posterior estimations, and it has wide application in machine learning, where we try to represent the laws of denoising autoencoders, and we try to represent or use these applications in signal processing, where we have to transmit a signal irrespective of noise. We try to identify the segregate the part of signal which has more information, and we then try to transmit that part of signal. Moving on, we talk about mutual information applications. So we see the mutual information is represented represented by capital I, which represents the entropy, and then we use this information widely in different applications, majorly into the feature selection. So if we remember applying decision trees on any of the data where we try to select a feature, that which feature is going to act as a root of my decision tree. So how to identify is generally taken care by the three algorithms that we study in decision tree: ID3, CART. So these algorithms follow the information gain index and Gini ratio, which is again driven by the mutual information concept. So this is how we can apply the calculation of this mutual information into the decision trees and selection of feature for a wide range of data. Then we have wide applications in different other parts as well. Contrastive learning, we have privacy and security, where we can apply the concept of mutual information. Then we have neuroscience, where we try to encode the neural part. And then we have active learning, where some informative samples and selections are there. So how do we establish relationship between different quantities? We see the spiked Wigner model along with the concept of mutual informations represents some limits to detect the signal detectability. So here we can introduce MMSE along with the mutual information that can link the best estimators to identify a representation of a signal. And then we have the concept of information theory, which presents fundamental estimations and statistical estimations for learning and representation of my information theory concepts. Then if we check in high dimensional inference, where we have fundamental and achievable bounds, so there also we try to identify the concepts. So now why we are studying so much of mathematics, or we have been doing the various derivations yesterday in tutorials as well. So today we will see how these models can be applied into the different range of applications. One application in digital communication presents a foundation of wireless and wired networks, where we widely applied the concept of information theory and mean field theory of high dimensional Bayesian inference. Then in the concept of machine learning and AI, we try to identify feature selections. Likewise, I said in decision tree, we try to identify which feature should represent a root. Then we try calculating the entropy and information gain of all the features, and then we come on finalizing the selecting the feature that represents maximum information. So that is the representation of mutual information in context of decision trees. So then we will see how in cryptography and network security, the mutual informations and information theory plays a role. And then we have neuroscience and biology following the big data and IoT. So let us see in digital communications, it ensures the error-free data transmission. So whenever we talk about communication, we talk about how our information is transmitted from one source to the destination without the any loss, and without introducing any extra noise in the information or in the signal. So we generally follow error-free data transmissions, and there are many algorithms that we follow in order to correct the codes. And then we also follow the compression part. We try to compress the data before transmission, where we follow Huffman coding, arithmetic codings, and there are many such techniques that we follow in digital communication, which are also driven by information theory concepts. Then we have the modulation and capacity. We try to also modulate our signal so that it represents the best form, which helps in optimal modulation schemes. It determines again the Shannon entropy capacity, also followed in our modulation and capacity part of digital communication. Then we also follow digital communications in wireless and 5G and emerging 6G networks. So now Information theory is also bridging the gap between applications of machine learning and underlying the mathematical frameworks which play the major role in training the data in machine learning based applications. So we try to see information theory which quantifies the uncertainty and which identifies the information part efficiently from the network. So this machine learning deals with the data-driven patterns and recognition and decision making. So here are the key connections. The information theory concepts helps in identifying the capacity of a model, identify how uncertainty or how much noise is there in a signal while training a model, and then we also deal with efficiently representing and training the model and checking on the concepts of accuracy and different evaluators, where also information theory concepts plays a major role. Then we have wide applications in feature selection, in regularization, in deep learning interpretability, and there are many generative models we utilize these days have also been backed up by the concepts of information theory and entropy. So if you see here information theory and entropy, in case of a machine learning, we try to identify entropy, which represents the measure of uncertainty in a random variable, and then we try to reduce this randomness by calculating the information gain, and then we try to split the different variables, and this is how we prepare a decision tree. So this is what I was talking about, how information theory plays an important role to identify the best estimators to become a root node in case of a decision tree, and also has wide applications in the different parts of decision tree, for example random forest and various other ensemble based methods. So this mutual information represents the dependency between the random variables, which has a tendency to select the most suitable features to break down the tree, so that we have highest mutual information with the output variable, which will result into the better models that we try to train. So sometimes we are not aware of that what type of feature selection algorithm we are using and what type of information. We generally follow the default settings. So with this information on information theory and knowing the mathematical background, it will assist us in identifying that how we can employ the optimal feature selection for the set of code or for the training or for any problem that where we try to employ the concept of decision trees or any machine learning model into a problem. And it also follows the applications in dimensionality reduction, where we have high dimensional data and we try to reduce the data into a low dimension, and then we try to represent this information in a compact form. So changing the dimensions or reducing the dimensions also has wide applications. So we also introduce a concept of information bottleneck and regularization. So if we remember applying linear regression, so down there also we try to compute some coefficients that we are going to see in this part, in the next part of our course as well. So there we introduce some regularized coefficients that regularized and also handled underfitting and overfitting of my model. So the goal here is to maximize the information bottleneck while minimizing the error where T represents. So where we try to minimize the error, this here represents we can follow information theory concepts in identifying the different layers of my deep neural networks, and it also helps in preventing overfitting and improving the generalizations which we generally follow in our linear regressions and generalized linear models. So following up, we have some advanced applications of information theory in machine learning as well. We see there is a concept of clustering. So clustering represents an unsupervised form of learning where we are given different data points and we try to identify to which particular cluster these data points follow. So we follow certain algorithms, maybe some distance based heuristics or some other algorithms, where we try to identify all the objects with similar measures into the one category, and then we try to identify the different parts into the one part where we try to check. So where we try to check how well we can identify an object belongs to which cluster based upon the heuristic that we are following. For example, we try to calculate the nearest neighbor, k nearest neighbor clustering algorithm, where we try to identify all the objects which are falling into the range have the similar characteristics, and we identify the algorithm identifies the objects into the same domain as a one cluster. So here we are not having any type of labels or any type of supervised learning methods into the picture. So if you see here the introduction of variational autoencoders and the uses of generative AI, the generative adversarial networks also follow entropy based metrics or information theory based metrics to evaluate the performance of models or to evaluate the process of data augmentation that we also follow nowadays as an emerging technology. Then we have another part, that is reinforcement learning, where policy of entropy encourages the exploration. So if I explain, in case of reinforcement learning, we are not having the exact labels, but we do have some rewards while attaining the better performance. So as soon as the model tunes to the best estimators, we have some activation functions to reward the model so that it learns in an auto mode and without having any supervised labels, in order to introduce the reinforcement learning part. So majorly all the games or game theory that we follow falls under the category of reinforcement learning that we follow. So having said enough about the role of information theory in digital communications, in machine learning, now we will see how information theory plays a role in cryptography and network security. So if we all know, cryptography is the art and science of the part where we try to identify the how securely we can transmit. So in digital communications, we just talk about sharing or transmitting a signal. In cryptography, we talk about how securely we transmit a signal such that nobody hampers or nobody destroys the signal and there is no attack into the network or independently on the information that we are trying to convey. So in cryptography, we always follow secure communication principles, and the theory of Claude-Shannon's information theory entropy concept has been widely used in the concept of perfect secrecy. If you see, there are many concepts of information theory. The confusion and diffusion part is also followed in cryptography and network security, where we try to transmit a signal with the help of applications of multiple cryptographic algorithms, and these algorithms are again based upon the concepts of information theory. And there are many security matrices which are based upon entropy and mutual information. And there is one more concept here I would like to introduce, which is the steganography. In case of cryptography, we try to convert the actual message, the plain text that we refer in cryptography, into the ciphertext. Whereas in steganography, we try to and then we transmit this stago image over the communication channel such that no quality information is lost and even the opponent is not able to identify that some information is being transmitted, because we have hidden the information into a cover image. For example, I wanted to convey a key from one source to the destination. So instead of encrypting the key, in case of steganography, I will hide this key into an image or maybe an audio or a video, and then I will transmit that image, audio or video. So now receiver will receive my video which is having some part encoded into it. So all these techniques, the least significant bit, and there are many more steganographic techniques that we follow, and also has their background of mathematical frameworks which relates to the information theory part of our information theory part also plays a wide role in identifying all those parameters to transmit the information. So if you see here, the Shannon entropy has been introduced, which measures the unpredictability of information. That is also widely applied into the areas of cryptography, where we try to achieve the perfect secrecy. So if those who are working in cryptography may be able to relate, for now there is no such algorithm that is uncomputationally secure. We always try to identify a computational security and cost whenever we try to devise a cryptographic algorithm that converts our plain text into a ciphertext, and also we try to achieve the perfect secrecy. So here the ciphertext reveals no information about the actual message, conveys the perfect secrecy in a optimal or in the best algorithm that we try to devise. So the condition that we follow here, how we can relate it to the information theory and probability science, that identifying the entropy or identifying the information is given any ciphertext, plain text is not recoverable. That means unless until we have a key or we know the algorithm, nobody will be able to identify the plain text out of the ciphertext, which is also represented here in form of probability in a condition h of given the probability of plain text given the ciphertext, and then we try to identify that it is only dependent upon plain text. So that means one time pad is one of the cryptographic algorithm that is now till now considered as one of a perfect secrecy example, but it imposes other challenges in order to deploy this algorithm one time pad into the systems or during the transmission. So this is how we can identify the role of information theory in sharing any signal or in identifying the mutual information. So looking at mutual information into cryptanalysis. So have we talked enough about cryptography and steganography? Now the term cryptanalysis is the part where we try to analyze the algorithm in form where we don't want algorithm to break down. So that means as an opponent we try to identify the security features of my proposed algorithm, and here also mutual information and information theory plays a role, particularly where we try to identify a brute force analysis, where we try to identify a side channel attacks, we try to identify a key leakage, we try to identify a opponent has got the somehow access of a key range. Then how can we minimize the information of plain text on ciphertext is what we follow in case of a cryptanalysis, and here also the mutual information is represented in one or other form in order to apply these concepts in cryptanalysis of any algorithm. The another part is key management. So whenever we talk about cryptographic algorithm, we have several keys. Majorly we have two types of cryptographic algorithm. One is the symmetric key, another is the asymmetric key. So in symmetric key algorithms, we follow one key. The same key is used for the encryption at the source when a signal is to be transferred, and the same key is used at the destination site where the signal will be recovered by using the same key. So it has its own pros and cons. Whereas in case of a asymmetric cipher, we have two set of keys. One key is used for encryption and one key is used for decryption. So we have separate set of keys. So when a user has separate set of keys, we need an agency or we need a third party that will be managing the keys. So here comes the role of key management in cryptography. Whenever we have to distribute the keys, down there also entropy plays a major role to identify the randomness and the noise-based systems. And keys, it is referred in cryptography, in key management infrastructures, that these keys should have high entropy to resist for brute force attacks. Now, what is the meaning of brute force attacks here? We try to employ all set of keys on the algorithm to identify, can we recover a readable plain text from a given ciphertext without knowing the key. That is the cryptanalysis of any algorithm with the help of a brute force attack. So here also we follow the concept of entropy, where we say all the keys that we are using of either a symmetric or asymmetric keys should have high entropy to resist the brute force attack. So information theory also plays another role in evaluating the randomness in key generators. So there are many algorithms where we use any random number, and this random number follows the different algorithms. For example, RSA, we follow a large prime number. So identifying the randomness in all those key generators, information theory again plays here a major role, where we try to identify that how well we can make key management in cryptographic systems by following these frameworks. So if we see the modern cryptographic systems such as quantum cryptography, multi-party computations, secret sharing schemes, or some resilient cryptographic techniques, so all these techniques are also ensured by the concept of information theory and unlimited computing power against the adversaries, so that nobody is able to hamper or modify the information that one source is trying to transmit from one channel to another channel with the help of any cryptographic algorithm applied to the plain text. So this is all we represent the role of information theory in cryptographic systems. So coming to the next part, where we try to represent the role of information theory in neuroscience and biology. So information theory also helps to quantify how biological systems process, transmit, and store the information. So there are cognitive systems where we try to nowadays simulate the computer-based neural networks, also like the computations of our brain or a human mind. So neuroscience is the science which deals with the neural encoding and the brain communication of all these informations, and how the information is processed, transmitted, and stored. So in case of biology, we study the generating information, the molecular interactions, the biological part. And in case of information theory, the role of information theory is to understand the efficiency, robustness, or the complexity of these biological systems or these information systems that we are trying to build, which mimic the human mind. And we try to come over these applications where we try to identify how well we can mimic the mind of a human brain with the help of neural networks or any part of the machine learning that can play a major role in taking a decision based upon the different learning experiences that we provide as a input to the model. So here the entropy quantifies variability in the neural spikes, and we can identify these spikes by the different information theory models. So it uses how much information neuron encode about any action, about any stimuli. So higher is the entropy, represents more capacity for information representation in the neural networks. So it helps in decoding the brain activity using different types of EEG signals, or maybe some different electrophysiology, or maybe some other types of signals that can be better represented if we understand the concept of these coding and information theory models. So in brain communication also, mutual information measures how well a neural response represents a stimuli. That means how it is used to map the stimulus response relationships in any sensory systems. So it also has wide applications in visual, auditory, and motor cortex analyses. And mutual information also helps assessing effective connectivity between the brain regions, and it also plays an important role. So we generally keep on applying these models into cryptography, into neural networks, or into the neuroscience or the biological sciences, or even into the machine learning. So we never undergo these underlying mathematics, which represents how we can change these frameworks, which can introduce any type of fundamental contribution to our research. To those who are doing some research based part, we can also follow these methods or these frameworks, which can be really helpful in identifying, or it can really enhance your maybe for graduation students, it can enhance your capstone projects that you do, the MTech dissertation part that the students follow, and the PhD research. So we always keep on applying from the application layer part, whereas Professor John Barber is trying to connect all those applications with the mathematical frame. And that is why I thought of talking about all those models can be applied to the different themes, how and when. So talking about the applications, so we have the brain computer interfaces. Neuroprosthetics rely on the different information theory principles. We have synthetic biology, evolutionary biology, and the future lies in integrating information theory with the artificial intelligence models to model a brain inspired computing, which is nowadays very emerging technology among the researchers to work upon. So those who are looking for a problem statement for their masters or PhD, they can check how can we apply information theory and AI to model brain inspired computing. So this is all for the applications of information theory into the biological systems or the neural science systems. So now moving on to talking about role of IT in big data, role of information theory in big data and IoT based networks. If we see information theory, it represents a mathematical framework which represents to measure information and quantifying information into the different addresses. So whereas a big data poses its own challenges, if we talk about big data, you see here we talk about volume, variety, velocity, veracity, and now these V's are extended in many other domains. So that means when we don't have a structured data, or we are not having a well quantified data, rather than we are having a streamlined data which is not following a quantified structure, which is larger in volume, has more heterogeneity, we are unable to represent this data by means of a database systems. So down there we follow the big data paradigms, we follow the Hadoop based distributed file system to store this data, and here we can also again employ all the information theory frameworks into the data compression, where we try to efficiently store this large heterogeneous data. Then we have noise reduction, we can clean and identify the usable or the more interesting data by reducing the noise out of the signals that we have when we have to store the data. Then the transmission efficiency, which optimizes the data flow across the networks. So this is where we say the use of entropy coding in the data lakes for the compression has also played a wide role in storing this big data into the frameworks. So this is how all these models can be connected to the big data systems, where we have larger amount of data and we try to store these data into the different nodes following the Hadoop based distributed file systems and MapReduce frameworks to work upon these different parts of information that we try to store. So talking about IoT, IoT devices generate huge continuous data, and information theory enables this smart in data encoding to save the bandwidth, because nowadays we have so many IoT devices and sensors which then generates a streamlined real-time data which we are unable to handle, and there are so much huge continuous streamlines of data that we need to know which part of data to store, which part of data to compress, and how to identifying the different transmission errors into the data. So if we see the role of information theory, we can identify the data encoding, the reliable communication, and the detection and correction of transmission errors. So these applications have smart homes, autonomous vehicles we have nowadays, wearable technology, all the smart watches we are wearing, we are having the smart machines as well, smart ACs, smart washing machines. So they detect and identifying the correct signal, and here also we can apply signal theory, information theory, which can play a vital role in the applications that we work upon. So following on, it also reduces the storage and bandwidth needs. It also offers smarter decision-making systems. It enhances the scalability in analytics infrastructure. So this is how we can follow the big data and IoT-based networks can also employ these information theory and high-dimensional frameworks for Bayesian inference to identify and to propose any methods that can have a optimized representation of storing this huge data into the system. So with this, I will stop here, that this is how we can relate that what all part we are going to cover we have covered in the last lectures, and what all mathematical frameworks we are going to cover into the next part. So with this, I hope I try to convey the part that how well we connect from uh, the models or the Bayesian inferences or the theory, that part we have covered, and this is how we can relate it to the different applications ranging from machine learning, cryptography, biological systems, big data, IoT, etc. So this is all I wanted to present, that how the information theory and these spiked Wigner model and mutual information can play a role in our different applications that we are working on. Okay, so with this, is there anything anyone wants to say? Or maybe anyone is on their camera, we may take one screenshot.
Is any questions from the audience side? Any questions from the audience side? Any questions? Any questions? Any query?
Okay, then I think at 11:40 John Barbier will join. So
projection पे
I think somebody has their mic on. So I request everyone to please mute themselves. Okay. So should we stop here?
Thank you, Dr. Jaspal. Started journey. Firstly, I replace Pooja and Jaspal with your mic. Please switch off. Please switch off.
Okay, I will mute. I will mute all.
So thank you. Thank you so much, Dr. Jaspal. We started today's journey with you, and you discussed various concepts.
पर आपने तो अपना पार्ट एक्सप्लेन करना ही था, मैम करने ही नहीं थी.
I think someone is talking.
All now.
Am I audible?
Yes, ma'am. You are audible.
Thank you, Dr. Jaspal. We started today's
Okay.
journey with you, and you
Okay.
discussed
Thank
a
you.
lot about the information coding, compression technique, cryptography, ML, neural networks, and you touched a lot of topics like big data, role of machine learning, even neuroimaging also. So it was great, and thanks for the informative session. And now we'll join at 11:40 with Professor John Parker. Okay,
ठीक है.
so
Okay.
all of
Thank you.
you